So, thank you very much. I want to present some basic notions connected with von Neumann algebra. Well, so let me look on the second page. It's this. No. Okay. So let me say that von Neumann algebra is used for description of any quantum system. It's algebra of operators in a Hilbert space, closed in a special topology, and mostly connected with von Neumann theory of measurement. So, in particular, any self-adjoint operator in such algebra is interpreted as a physical value, and any projection is interpreted as a physical question. So we have physical observables represented by self-adjoint operators, and physical and questions represented by projections. Each projection is connected with a subspace of a Hilbert space, and most of them, additionally, it's important that any such von Neumann algebra can be represented as some kind of integral using elements, some elements being von Neumann algebras, which are so-called factors. Examples of such factors are full algebra of all operators in a Hilbert space, but a great result of von Neumann was that there are some other special von Neumann factors, mostly described by special states. It means functionals such as a probability on events, and these states which has an additional property that they are tracial is very important to describe a von Neumann factor. In fact, it is connected with dynamics of quantum theory, namely equivalent projections are such that that we can move from one projection to another using some dynamics connected with this physical system. And if we look at such a von Neumann algebra describing a quantum mechanical system, then we see that then we look for some connection between fundamental notions formulated here. So in fact, is it possible, first question is it possible any self-adjoint operator and a physical observable as a finite real linear combination of projections in this algebra? If the answer is positive, then the question is if for such algebra there exists a smallest number n such that each observable can be represented as a linear combination of just n projections. It means just n quantum questions. And then if answer is positive, then the next question is what is the smallest n good for all von Neumann algebras or for some class of von Neumann algebras? And then we should look on special types of such algebras. And so let's go on. The first question is eventually true when M is finite dimensional, And also, if I take, in fact, all operators in finite k-dimensional Hilbert space, it's just this second case, then we also has a possibility of representing any operators using just k projections. But for example, if we take all functions, all bounded functions on any measurable space, that such complex valuate functions also present some von Neumann algebra. It means that this von Neumann algebra model describes not only quantum physics, but also classical physics and mixing of quantum theories integrated with respect to some some classical parameter. So in fact, if I take in my lecture, if I look on a very simple example, L infinity space, then it is a von Neumann algebra such that obviously the typical self-adjoint operator cannot be expressed as linear combination of finite number of projections. But it's interesting that we have some quite general results. They was obtained in 1992 by me and S.Goldstein. And they say that if only that any algebra if only that all depends on the center of the algebra. So if we have one factor, then always operator can be represented as finite number of projections. And if I take a integral of such von Neumann factors, then all depends on the space and a measure using in this integration model of the algebra. And this the first result is complete description of this situation, and the second result is formulated in the following way. Instead of real coefficients, we take coefficients from the center of algebra, and then the answer is always positive. Any operator can be represented using coefficients from a center of algebra by the use of finite number of projections. So it was these results now has about 30 years, but in fact many results we obtained just in the last 2 years. So the first time I want to show some history of the problem of representing self-adjoint operators as linear combination of projections in the algebra of all operators in a Hilbert space. So its theory started in 1937, and now after the work of Rabanovich from 2016, we know that always that the crucial number is 4, namely any self-adjoint operator can be represented as a linear combination of 4 projections. If we look on infinite dimensional factors, then the situation is quite different. Let me look on the next page. M is infinite factor. So a natural direction in the theory is to look on von Neumann factor. It means on such special algebras which is used as some bricks to build all von Neumann algebras. Algebra of all operators in a Hilbert space is a good example of such a factor. But as I said, the great achievement of von Neumann is discovering of some other factors connected with special properties of traces, and in particular, and after this result of Rabanovich, we have also results for other type of factors obtained just 2 years ago, and we know that in each factor to infinity we have 4 projections for each operator, such that operator can be represented by a linear combination of these projections. It is also, if we take the very important type 3 factor, very symmetric factor, von Neumann factor, then unexpectedly any operator being self-adjoint can be represented as a linear combination of 3 projections. The special method obtained in this result suggests that if we take a remaining factor of type 2-1, also each operator can be represented as, in this case, 4 projections. Any self-adjoint operator is a linear combination of 4 projections. But in published papers, we have the best number 12. But we know that that 4 is also good in this place. Well, people also solved the problem completely, the problem in finite factors. Here we look, in fact, on full algebra of all operators in a Hilbert space, in case when dimension of the space is 1, 2, 4, 5, 6, 7, any k from 8 to 75, and for k with k greater than 75. So in such dimension of Hilbert space, if I look on any operator, in fact, in this moment, we look on self-adjoint matrices in space of such a dimension, then the number of projections which then such number n, that always we have n projections and the combination linear of these projections, which is just exact this operator. So this n depends on the dimension of the space in the following way. So it is precisely described only for k between 8 and 75. We don't know if it's 3 or 4 up to now. But it's a special, but it's a specific theory of finite matrices. Let me explain theory in any Hilbert space. Okay. Okay. So now I want to present some precise theorems connected with this number n. And it's interesting that if I take a factor 1k, then I can obtain quite canonical form of representing of self-adjoint operator A as a linear combination of four projections P, Q, R, and S. These coefficients are quite canonical, but they depend on the trace of operator. So it's impossible to obtain arbitrary coefficients, any arbitrary in some interval. This is the situation in factor 1k, and in other factors 1 infinity or 2 infinity or 3, we always can use. We can always express self-adjoint operator A as a linear combination of four projections with completely canonical coefficients. So here we have some set of coefficients which can be used in any case. The only assumption is that obviously the norm of operator decides of the size of this coefficient. So, for example, if I take operator with norm 1, then this theorem gives completely some class of coefficients which can be used here. And now 3 important methods in proving theorems of such types. The first method is very fundamental knowledge about two projections in a Hilbert space. In fact, we can look on this theorem as a theorem on two projections in a Hilbert space. And if I take two projections which are equivalent in sense for us, we can look on this as some dynamics in this quantum system. So if the two projections are orthogonal and connected by some dynamics of this quantum system described by Hilbert space, then for any operator dominated by beta times one projection, we can describe projection operator, we can express projection D, and mirror reflection of these projections put it in the orthogonal part of the space by difference of two projections. So any operator can be naturally expressed by two projections. It's the first lemma, and this lemma leads to a method of giving positive results on construction of these linear combinations of projections. Here is a proof of this lemma, which shows that we can obtain the result in completely constructive way. It is simple way to write these projections. Then I want to speak about the second method, namely in this miracle result that in type 3 factor I can use only 3 projections to express any type, any operator. We need the general form of combination of two projections, namely, if we have proper description of all combinations of two projections, then we can work as follows. We can show operator such that adding any projections leads to some operator which does not satisfy this condition, and condition written here, namely it is conditioned on say, distribution of an operator. And if we look on distribution of an operator, being in fact distribution of quantum observable in physical language, then this is the general form of observable being linear combinations of two projections. So this method is very elementary and important in quantum mechanics as well. This line is symmetric with respect to this point. So this is the second method. And in fact, if I so in this way we can show some operator which cannot be expressed as combination of three projections, but in factor of type 3 we have a possibility of representing any operator as a combination of three projections. And the main idea is that in such factor, it was great discovery of von Neumann, that in some von Neumann algebra, any projection is equivalent to any other projections by using of some quantum dynamic described by this von Neumann factor. And this leads to the solution of such type. And additional methods are especially interesting because they give some general results connected with solving some equation in operator algebras, and could lead to a number of other methods. But I think that it's a good moment to finish my talk. So I want only add three titles of our articles, and thank you for your attention.
Thank you. Do you have any questions? Any comments?
Can you give any very detailed physical examples of situations where you can show your results?
Okay. As I said, it's only a relation between fundamental physical notions. My talk is just mathematics. It's just theory of von Neumann algebras.
Okay, I understand. So I mean, it would be very good to in future maybe to show very explicit examples of usefulness of your result for particular cases, you know, since it's like okay, it's quite general results, so I would say just from audience point of view.
Any question? Next questions?
Okay, maybe another. Okay.
Yes.
Is there a
Yes.
possibility to make a short point regarding?
Could you increase volume or?
Can you hear me well? My name is Jacek Leskov and I just joined the conference. Can you hear me well?
Yes.
Yes. It was very exciting to see possibility of, I'm not a specialist in quantum mechanics, but I do work with Hilbert space as a tool for statistical inference. And my forthcoming talk in a few minutes will be partially dedicated to that. And I'm especially looking forward for application to data dimensionality reduction, the results that were presented in Professor Paszkiewicz talk. Is there any possibility due to the speaker to have this type of application, dimensionality reduction for, let's say, Hilbert space-based data analysis?
Well, say not in this moment. In fact, here I speak only on some geometry of operators. it's rather far from any. Well, I know there is a number. Okay, knowledge on projection in Hilbert space leads to many applications. All linear models in statistics and are in fact can be treated in this theory. Such notions as stationary of processes are connected with projections in Hilbert space. But the answer is as follows: we need knowledge, we need methods connected with projections all the time. All the time we know very few about projections. Let me say that when I present